Welcome to Hydrogeology 101. My name is Andres de Jong, and in today's video I'd like to introduce you to resistivity surveys. I hope you enjoy it.
We would like to find the best location to drill a water well in this alluvial aquifer. One option we could have is to bring along a drilling rig and drill an exploration well every 20 meters or so. Maybe we'd find the right place, maybe not. It would waste a lot of time and, more importantly, a lot of money because drilling is very expensive. So is there a cheaper option? Yes, there is. It's called the resistivity survey, which is the subject of this video. First of all, what is resistivity? If we have an electrical circuit, the electrical resistance R of a wire in which current I is flowing is given by Ohm's law. R equals V over I, where V is the potential difference across the wire. R is measured in ohms, V in volts, and the current I in amperes. The flow of electricity in a wire can be visualized as a pipeline filled with flowing water. The current in the wire is equivalent to the discharge of water in the pipe. The resistance in the wire is equivalent to the friction losses in the pipe, and voltage across the section of the wire is equivalent to the pressure gradient in the pipe. There is a problem with resistance. If we increase the length of our wire, we increase the resistance. If we increase the area of our wire, we decrease the resistance. What this means is that resistance is not a fundamental characteristic of the metal in the wire. Now, the resistance is proportional to the length of the wire and inversely proportional to the area. We have a constant of proportionality called resistivity, and it is usually shown as the Greek letter rho. Resistivity is therefore a fundamental physical property of the metal in the wire. Resistivity is the property which we're trying to measure with resistivity surveys. Resistivity is the resistance per unit volume, and it is measured in units of ohm meters. If we have a unit cube of 1 cubic meter and we have a resistivity of 1 ohm meter, what this means is that if we have a potential difference across it of 1 volt, we will get a current flow of 1 amp. Here are the resistivities of some typical rock-forming materials. The scale is logarithmic between 1 and 10,000 ohm meters. As a rule of thumb, if we have less than 10 ohm meters, we're dealing with either a very clay-rich formation or a formation that has salty water in it, or both. Most aquifers are in the range of say 10 to 500 ohm meters, but they can be higher, for example in cemented gravels. When the resistivity exceeds about 1000 ohm meters, we're generally in bedrock with little chance of productive aquifers, with the exception of some fractures. Normally, it's not possible to measure resistivities above 10,000 ohm meters. Let's have a look at some resistivity equipment. This is the ABEM terameter from Sweden, which I've used a lot in Oman and also in Ghana. It's very lightweight, robust, and it can last for years. Here we are in Ghana looking for some basement fractures. A big hello to Edwin if you're watching. This is the Cisco Pro from Iris Instruments of France. Here we are in Kabul, Afghanistan, doing a survey next to MRD. Hello Engineer Jalil if you're watching. It doesn't really matter which resistivity meter we have. The most important thing is the geophysicist, his team, and how they do their field procedures. You're going to need a good power source. Normally it's some batteries, sometimes it's a generator. You're going to need some good, well-insulated cables to take the current to your 2 current electrodes. These are called A and B. And when everything is connected, we can inject current into the ground, which we measure in milliamperes. Another thing we want to measure is the potential difference between our 2 potential electrodes. These are called M and N. The potential difference is measured in millivolts. Of course, we're going to need a bit of shade if it's very hot to protect both ourselves and our equipment. We're going to need some transport, And very important is our field team. You're going to need at least 2 workers in the field, but better is 4, because then you can speed up your survey. They'll also need a lot of water to put on the electrodes. Let's go back to the example we looked at earlier. We'll assume that our alluvial aquifer here has a lower resistivity than the underlying bedrock. We're going to bring our equipment to this side of the valley, and we're going to plot our apparent resistivity values against distance. Now, the first reading we take at the edge of our valley, most of our current is flowing through the high resistivity bedrock, so overall our resistivity values will be quite high. As we move along, we're still close to the bedrock and we have high resistivity values. Now, as we move into the area of the valley where our alluvial aquifer is thicker, we're going to have a bigger effect of this low resistivity material. So our overall apparent resistivity will go down. And you can see that in the thickest part of the alluvial we have the lowest apparent resistivity. Now, as we reach the other side of the valley, we start to see the effect of the basement rocks, which are approaching the ground surface. So we're going to have more effect of this high resistivity material, and our apparent resistivity increases. What we've just completed is called an electrical resistivity profile. And we can join up all our little dots and think of it as a kind of picture of the subsurface. Now, if we're looking for the lowest resistivity anomaly, then we would decide to drill right here. However, how deep should we drill? To answer this question, we need to do what's called a vertical electrical sounding, otherwise known as a VES. Here is the same resistivity equipment, and we are going to plot the apparent resistivity in ohmmeters against AB over 2. Now AB over 2 is half the distance between the 2 current electrodes. We're going to assume we've got 2 layers here. This is row 1 for the upper layer and row 2 for the lower layer. What it means is that our upper layer here has a higher resistivity than the lower layer. Now, the first reading we take, we're mostly in our upper layer, so we have a resistivity of row 1. I should say an apparent resistivity of row 1. Now we're going to move our current electrodes slightly apart, take another reading, move them a bit further apart, take another reading. We see that as we start to approach this bottom layer, maybe the resistivity will drop off a little bit. But at this point, our 2 current electrodes are quite far apart, so it's getting difficult to measure the potential difference between M and N, so we're going to increase the distance between them a little bit. And just to be sure, we take another measurement to see that nothing has changed in this upper layer. Now we increase again our AB spacings, take another reading, increase the spacing again, take another reading, and increase our M and N again. Do a check to see that nothing has happened. You'll notice that now we're really getting into this lower layer. So a lot of our signal is coming from the row 2 layer. So that means that our apparent resistivity curve is starting to drop off towards this lower resistivity. So we increase again and take another reading. Now, this is called a vertical electrical sounding. Let's have a look at our main electrode arrays. Electrode arrays are the way we position our current and potential electrodes. This configuration is called the Schlumberger array. In the Schlumberger array, the distance between A and B, the 2 outer electrodes, has to be at least 5 times the distance between M and N. Now we calculate our apparent resistivity by measuring the delta V and I, or multiplying it by K. K is a geometric factor which is dependent on the configuration of the array. Another array that's used a lot in groundwater exploration is the Venn array. In the Venn array, all the distances between our electrodes are constant. The formula is the same, but the geometric factor is slightly different. Now, I only use the Schlumberger array for groundwater exploration. There are three reasons for this. The first one is it's much faster because normally we only have to move our two outer electrodes. I mean, sometimes we do move the inner electrodes, but not as often as if you were doing a Venn array, which means you have to move all four electrodes for every reading. Another reason, which is actually the most important reason, is it's much more accurate because we can change our M&N and A and B electrodes separately, so then we can cross-check if there's been any lateral variations in the near-surface resistivity, which can lead to errors in interpretation of the VES. And last but not least, and this might surprise some of you, it has a slightly deeper depth of investigation than the Venn array. Let's have a closer look at the depth of investigation, a term that has led to a lot of confusion. The depth of investigation is difficult to define, as it depends on how the currents propagate in the subsurface. Let's say that we have a VES with an AB spacing of L, and Z is the depth below the sounding. If we plot Z over L against the response, you can see the relative contribution to a VES measurement from the different depths. Note that the measurement that we make is the total area under this curve. So a lot of it comes from this area, but there's also some coming from down here and some from the top. Now, there is a depth at which we have the maximum response, but note that actually most of the response comes from below this depth, so it's not very useful to use this parameter. It's much more useful to take what's called the effective depth, which is the depth at which half of the measurement comes above this depth and the other half comes from below. We could also call it the median depth of investigation. Okay, so to summarize, the effective depth, or the median depth of investigation, is the depth from which we get 50% of the measurement above that depth, but there's always another 50% which comes from below it. The effective depth divided by L for the Schlumberger array is 0.19, where L of course is the AB spacing. For the Venn array, we have a number of 0.519, and some people seem to think that that means the Venn array has a deeper effective depth. But of course it refers to A, which is only 1/3 of L. So what we need to do is compare the two arrays side by side and correct the formula for the Venn array, and then you can see that the effective depth of the Venn array is actually less than that of the Schlumberger array. Just to give you a practical example, if we have an AB spacing of 300 meters, then in the Schlumberger array we can expect an effective depth of about 57 meters, while for the Venn array it is 52 meters. So not a big difference, but the Schlumberger array is slightly better at going deeper. Now, all these theoretical calculations assume a uniform Earth, where the electric currents can go downwards and outwards as they please, and there's no change in the resistivity. In the real world, we can have an example like this, where there's a lower resistivity layer at the surface, and what happens then is that more of the currents will stay around in this layer. Because if you remember Ohm's law, if the resistance goes down, the currents go up. So in this case, the effective depth will be much reduced because the currents will hang around more in this upper layer. The reverse is true. When the surface layer is more resistive, the currents try to get through it as quickly as possible, so they generally go downwards to find a more conductive layer at depth. Now, the rule of thumb is that we should have a depth of investigation which is about 1/3 of the AB spacing. What it means is that if you want to look down to 100 meters, your AB spacing should be at least 300 meters. Of course, the current goes much deeper than this, but down here the relative response might be too weak to distinguish any new layers. Okay, let's have a look at what apparent resistivity curves look like. In this scenario here, we have a resistive layer at the top overlying a low resistive layer below, and the top layer has a thickness of 10 meters. You'll notice that the apparent resistivity curve, it starts at 200 ohm meters, which is the resistivity of our top layer, and then it goes through a kind of a transition phase before it joins the resistivity of our lower layer of 10 ohm meters. That's why it's called an apparent resistivity curve, because this is the real resistivity, but this is what it looks like in our VS sounding. Now, let's change the bottom resistivity to 25 ohm meters and 50 ohm meters and 100 ohm meters. So all of the resistivity curves start at the same place because the top resistivity hasn't changed, but as we change the resistivity of our bottom layer, it gradually brings the curve up to meet the resistivity of our second layer. In this case, we have a low resistivity top layer overlying a more resistive second layer. You see that it starts at 10 ohm meters and it goes towards our 50 ohm meter second layer. Let's change that to 100 ohm meters and 500 ohm meters and 5000 ohm meters. What I'd like you to notice is that the curve starts to approach what is actually here almost a straight line, which is going up at 45 degrees. When we have an infinitely high resistive layer at depth, then we will get a 45-degree line. It cannot be steeper than 45 degrees. So if you're in the field and you start getting values up here, it means there's something wrong with your survey. Okay, in the third case, what we have is a 500 ohm meter surface layer, then a 250 ohm meter middle layer, and then a 50 ohm meter bottom layer. Notice how we can't really see this 250 ohm meter layer. If we change the bottom layer to 100 ohm meters and to 500 ohm meters, 1000 ohm meters, you see that we start to see this kind of a bowl shape in here, which is our second layer. Now, here's a scenario where we're going to just change the thickness of our second layer. This is the typical kind of curve we'll see over weathered basement rocks, where we have resistive soil at the top, a weathered zone, maybe laterite, and then basement rocks underneath. So this would be our aquifer. Now at the moment it's 5 meters thick, 20 meters thick, 50 meters thick, and 100 meters thick. Notice how our bottom layer resistivity, this infinitely high resistivity straight line, is getting pushed to the right. At the same time, our weathered zone here, our second layer, is gradually pulling downwards. But notice that it's 50 ohm meters, but we never actually reach an apparent resistivity of 50 ohm meters. I'd just like to summarize what we can get out of a resistivity survey. We can get the depth of the base to the base of the aquifer, we can get the resistivity of the aquifer, maybe even some intermediate layers in here. And then when we drill the well, we'd also like to know what is the depth to our static water level, but that's something we should get from our baseline survey, because it's very rare to see that in a VES. Okay, let's have a look at some of the interpretation software. Before the days of computers, we used to use master curves And in my career, I only came across one guy in India who was still using them. That's about 20 years ago. Most people nowadays are using computers. For example, this 1D inversion software, 1x1D by Interpex Limited. And this one here is called GeoVS. It's an Excel-based software which I made about 20 years ago. I'll make a separate video about it soon. If we have lots of data, and I'm talking about thousands of data points, we can do 2D inversions of the apparent resistivity values using software like Resistivity Invert from Geothermal software. However, remember that these kind of surveys are much more expensive in terms of equipment, effort and time. They can only be justified for very detailed surveys, like if you want to map the entrance to the New Salang Tunnel in Afghanistan, for archaeological investigations, or sometimes if you're in a very complicated fracture zone. For groundwater exploration, resistivity profiling and VES are the fastest, cheapest and most effective methods to locate drill sites for water wells. There are also other methods like TDM and magnetic surveys, which we'll cover in another video. I just want to end with some good and bad examples. Earlier we saw our apparent resistivity curves are always nice and curvy like this. This is also what we need our data to look like. When the data smoothly changes, we can fit a curve through it and we have a very low error margin, and that means our resistivity curve is okay. But if we get a situation like this, where our data is all over the place, and basically our model has no purpose whatsoever. I mean, this model is just garbage. It doesn't help us at all to understand this aquifer. In this case, we should send the geophysicist back to the field, and if it's a contractor, don't pay for it. Well, that's all I want to say today about resistivity. I hope you've enjoyed it, and see you on the next video.